And welcome back to statics. So this time we'll be talking about the simplification of force and couple systems, as well as how we can do that in different ways. There we go. Now, when I say couple systems, you're probably like, wait a second, we're talking about relationships here, we're getting into couples, not that kind of couple. Though it is two forces, so a couple in that regard. So first off, why do we want this couple moment thing? Well, we want it because we have a force that's acting on, let's say, some rod. But we probably want to figure out, what does the hand here feel? Switch it away. There you go. What does the hand feel? Not what does this end of the rod feel? So when we have a force that's in the line of action of the rod, or the line of action of the force is parallel to it, well, then I can just move that force over here. It's not that hard. However, in this case, I can't, because you realize that this force will feel, this hand will feel some twisting motion, some moment, because of that force. So if I want to move the force so I can see in one spot everything that's happening to what's holding it, to that support, to that hand, I would have to take into account the effect of the moment. And that's not hard to do. Other things we care about is with like these support beams. Like if I have several forces and moments all applied to this, is it okay? Is it going to survive all those forces and moments at this particular point? Do they all have some external effect on it? And is there a way for me to sum all this up into one nice force and moment system that has the same external effect? Hopefully, because that's what this section is about. So, how do we do this? Well, what we're going to be doing is we're going to take these forces, we're going to take these moments, and we're going to combine them into a force and couple system that is equivalent. And when I say it's equivalent, it means it has the same external effect on the body as the other forces, the set of forces and moments that we have replaced. Now, this is really super easy when the force is parallel or along the line of action of our rod, whatever we care about. So in this case, I can just move this force vector wherever I want. And this is what's known as a sliding vector, because I get to slide it along the beam. And I jumped too far, sorry. However, when we get to the internal effect, like what is the atoms feel of the bar, that does depend on where the force is applied, so we couldn't move it in that regard. So that's just the difference between statics and solid mechanics. Statics, you can figure out everything that's happening at a single point. Solid mechanics cares about everything all along the way. Okay, now here is a little bit more difficult case when we want to move a force that is not along the line of action of the rod, and therefore I'm moving it off of its line of action. When I do that, I can't just move the force. I can't just say, well, it was here before, it's here now. I have to take into account whatever effect this would have felt, the moment it would have felt from the force over here. So I had some distance, I have a force. It's really easy to calculate that moment. I just have to remember that when I move the force, however far I move it, I have to calculate the moment that this would need, that this would have caused if it was still in its original position compared to where it's moved. So I move it all the way over here, moment equals force times distance. It always comes back to that same exact equation. So it's not hard to do, you just have to remember. Moment equals force times distance. You move the force to where you want, pointing in the same direction. You figure out the distance between the 2 points of where it was before, where it ends, then moment equals force times distance. Now this new couple moment that you are adding to this is a free vector. That means that you can put it anywhere you want, including, in this case right here, the hand, because that's what I care about at this point. I want the hand to be where this moment is attached. And this is it. It's really not that hard. It's one of those things that I think you kind of have to see done a couple times before it really sticks. But for now, just remember, whenever you move that force off its line of action, you have to add in a moment that's equivalent to the force times the distance you've moved it. The perpendicular distance, of course. So with that, we'll stop here. And next time we'll learn a little bit more difficult situations with multiple forces and multiple moments, all acting on a single body. So I hope this helps you, and I'll see all of you next time. Bye-bye.